This week we're going to finish our discussion on Chapter 16 and look at another aspect of wave-like motion. In the first part of this, we're going to talk about simple harmonic motion and uniform circular motion. And what you can see here is a device that is set up in order to look at the effect of a circular motion on a horizontal movement. The circular motion results in a simple harmonic motion when you look at the shadow of a ball rotating at a constant angular velocity on a turntable like this. This results in or produces in this shadow below a what can be considered a simple harmonic oscillator or simple harmonic motion. Now this can be thus converted mathematically to look at the relationship between the movement through the circular motion, both the velocity as well as the effect of the radius of the circle and the radian motion into this x displacement that's seen in the simple harmonic oscillator. So as P moves along this path at a constant velocity, what happens is it projects on the x-axis a movement back and forth in a simple harmonic motion. The velocity at this point is projected, and these velocities form this triangle here, and this can then be calculated. So that's what we're going to do in this next slide. If you look at any point P, you can calculate the position or the displacement x by looking at the radius times the cosine of this angle theta, which is the angle that is separate from the original starting point. So x is equal to big X, which is the radius, times the cosine of theta. Theta, as we know in any circular motion, is equal to the angular velocity times the time. And therefore, x is going to be equal to the radius, which is also the maximum oscillatory motion, or the amplitude, times the cosine of the angular velocity times the time. And this, if we look at the angular velocity as a function of the period, then we can convert this formula into x at any time t is equal to the cosine of 2 pi t divided by the period. And this is the formula that we need to keep in mind as we look at calculations in this way. Now, you can also, as this moves, you can also plot this, and what you see again is something very similar to something we saw in our previous lecture, and that is a cosine wave. It begins at the top here. A sine wave would begin at 0. A cosine wave that cycles every period, capital T, and has an amplitude of x and negative x, large x and large negative x. And this graph plots the position x at any time t. So if we know that the period from our last lecture is equal to 2 pi times m divided by k, that m being the mass divided by k, the square root of that function, and that describes this as well. So we can use this formula along with this previous formula here to do some calculations. Now, as you well know, the real world does not continue in simple harmonic motion without any interference. The real world consists of forces that counteract the original force that occurs, and these forces are known as dampeners or dampening forces. And what we're going to talk about now is damped harmonic motion. This is a picture of a child, and in a perfect pendulum, no intervention would have to be taken. because this would continue to swing back and forth. However, because of friction and other dampening forces, the father needs to continue to put in force in order to keep the child swinging. Now, these dampening forces are the work required to keep the situation going is equal to the change in kinetic and potential energy that occurs as a result of the dampening force. So here's an example. You see the original amplitude is big X and the period is T, but what you see happening is that with each successive period, the dampening occurs more and more, and the size of the amplitude decreases more and more. This shows a small amount of dampening in that it takes several periods in order for the wave to get completely dampened. Now, critical dampening is a condition in which the dampening of an oscillator results in it returning as quickly as possible to its equilibrium position without oscillation. So what that means is that if critical dampening occurs, you pull the material to its position X and it returns to position 0 without any oscillation whatsoever. That's known as critical dampening. Underdamped is the system that overshoots the equilibrium position one or more times. And this is actually a normal situation where you'll pull it out beyond the equilibrium position and let it go, and it will swing back and forth several times before it stops. And that's called underdamped. Overdamped is dampening that causes a return to without oscillation, but causes it to return more quickly than critical dampening. So B here represents critical dampening, A represents overdamped. So the displacement versus time in critically damped oscillator, A is the critically damped, and overdamped is B. The critically damped oscillator returns to equilibrium position 0 in the smallest amount of time possible without overshooting. Now, what happens in a simple harmonic oscillator when there's dampening occurred is there's a transfer of energy from the original input into the oscillator into whatever causes the dampening. And in this case that we're looking at here, the friction causes the dampening. So let's say that we have this system pictured above, that K is equal to N 50 newtons per meter. The amplitude is 0.1 and the mass is 0.2 kilograms. If mu kinetic is 0.08, what is the force of friction? And then what is the total distance that the object will travel? Now, in order to do this, I need to open up the... Okay, first of all, in order to do this, we have to look at the friction force. Remember that friction is equal to the mu k times the normal. In this case, it's going to equal mu k times mg, which is going to be 0.08 times the mass, which is 0.2 times 9.8. And if we look at the math calculation here, we get 0.157 newtons. So that is the amount of friction force that has to be overcome to keep this object moving. Now, the second question here, basically what we have is we put elastic potential energy into the system, which is going to equal 1/2 kx squared. Now, over a period of time, this will be transferred into work, which is going to equal minus the friction force times the distance traveled. Okay? And we also know that this will stop at some point where the friction is equal to the force of elastic expansion. Now we already said that the friction force is equal to mu k mg, and we know that the elastic force is equal to kx by our last week. So that x, the point at which this thing will stop, is going to equal mu k mg over k. And so that's the point on the, whenever this relationship is equal, that's the point where it's going to stop. So this work of friction is going to equal the change in kinetic energy plus potential energy, which is going to equal the potential energy elastic minus the potential energy expended to overcome friction. And that's going to equal 1/2 K times mu, and I'm not going to put this little k in there every time. It's only, we'll just do that so it doesn't get confused with the other k, over k squared minus x squared. Now we also know that this is also equal to minus FD. So that this whole thing, minus 1/2 K mu mg over K squared minus x squared has got to equal MD, and we also know that that MD, FD, I'm sorry, is going to be mu mg times d. Now we can simplify this a great deal and solve for d, and we end up with k over 2 pi, or mu mg times x squared minus mu mg over k, this quantity squared. And if you put all the numbers in there and do the calculation, and I'm not going to write all the numbers in, but it's 1.59 meters is the total distance that it'll travel.